Okay, so carrying on with 2D momentum, in this video we'll be looking at a slightly more difficult situation where we apply 2D momentum concepts compared to the last video, but not that hard. I think it's still manageable. So in this video we'll be looking at when two masses are moving at different directions and they collide and then move off in different directions. So we can calculate the initial momentum and the final momentum using vector triangles again. So if we have a mass that's 5 kilograms, and let's move it down this way, let's say 2 meters per second. And we have a 4 kg mass, and it's moving this way at 3 meters per second. So this is our B4. And so the key idea for this problem is that in conservation of momentum, the center of mass of the system will be moving at a constant velocity before and after the collision, which we can see in our previous video. If we scroll up here, we said that another way to define the conservation of momentum is that the center of mass of the system follows Newton's first law, which obviously Newton's first law is an object will remain stationary or continue at a constant velocity unless acted on by a net force. In a closed system, by the way. So that same concept applies, where the center of mass of this system will probably be like right there, closer to 5 kg mass or the 4 kg mass, because 5 kg mass is obviously more massive, and so that will be our COM, and that's moving at a velocity of v. So we can say that the momentum of the center of mass, again with the vector hat, initially is equal to the momentum of the center of mass finally, again, because that's the law of conservation of momentum. So the key idea here is that the momentum of the center of mass is equal to the momentum of P5, which is the momentum of the 5 kg mass, plus P4, which is the momentum of the 4 kg mass. Now, we can't simply just add them together, again, because they're not scalars, they're vectors. So we still have to use our vector triangles to add those two momentum together, but that is the key idea. Momentum of the center of mass is the momentum of the entire system. And the entire system in this case is just the 5 kg plus the 4 kg momentums. Okay, so if we just draw up our after scenario, and then we can get right into this. So our after scenario, once they collide, we'll have the 5 kg mass going off this way, and the 4 kg mass going off this way. Right, and we have our right angle there. And let's say the 5 kg mass is moving at 1 meter per second. And for this question, let's say we're trying to find the velocity of the 4 kg mass afterwards. So if we know that the momentum of the center of mass is the same before and after the collision, we can use that to find out what that velocity is for the 4 kg mass. So we can calculate the momentum of the center of mass initially by using our vector triangles. So if we say this is our B4, we have the 4 kg mass moving this way, and that momentum is, again, P is equal to mv, so this will be 4 kgs times 3 meters per second, and that momentum is 12 kg meters per second. Right, and we have our 5 kg mass coming down this way. Again, P is mv. It's 5 times 2, and so that's 10 kg meters per second, right? And so the resultant vector, which will be the momentum of our center of mass, is coming down this way. Okay, this is going to be difficult. That's good enough. And that's our resultant vector. And so we have a right angle down there. And so using Pythagoras, we can figure out what the momentum of the center of mass is. And so that is just a squared plus b squared is equal to c squared, which is just 10 squared plus 12 squared is equal to p center of mass squared. Right, so 10 squared plus 12 squared is equal to momentum of our center of mass. And so 15.62 kg meters per second is equal to the momentum of our center of mass. There we go. And that's initially, right? So if we take our after and we draw a vector triangle for our after scenario, we have our momentum of our center of mass initially, which is equal to the momentum of our center of mass in the final. So we can just take that vector. I'm gonna just copy and paste it, but obviously if you're working on paper, you can't do that. But the momentum vector should be the same. That's what I'm doing. So we have our P0m, okay? And so we have our 5 kg mass coming out this way. So we can draw that right there-ish. And then we get a resultant vector coming down like this. So that is the momentum of our 5 kg, and that is the momentum of our 4 kg. Again, this is our right angle. And so we have the momentum of our center of mass, which is here. And we can calculate out the momentum of the 5 kg mass, which is mass times velocity, obviously. And that is 5 kgs times 1 meters per second now in the opposite scenario. And so the momentum is just 5 kg meters per second. So again, we can just use our Pythagoras, which is a squared plus b squared is equal to c squared. And so we can label this c, and this can be our b, and this can be our a. And so rearranging for a, we get a is equal to square root of c squared minus b squared. And so, sorry, that's meant to be a, not c. Okay, and so plugging it in, we get the momentum of the 4 kg mass is equal to the square root of the PCOM minus P5. Plugging in our numbers, we get, this is squared, sorry. Right, and now plugging in our numbers, we get 15.62 squared minus 5 squared. And the momentum of a 4 kg mass is 14.8 kg meters per second. And so what we're trying to find is the velocity of that 4 kg mass. So we know that P is equal to mv. We have our mass and we have our momentum, so we can rearrange for our velocity. So our velocity is equal to the momentum over its mass. So the velocity of 4 kg mass is equal to 14.8 divided by 4. And that is equal to 3.7 meters per second. There we go. So this scenario is slightly harder than what we did in the previous video because we had to draw 2 vector triangles and recognize that the vector line for the center of mass is the same in both before and after, even though the vector lines for the 5 and 4 kg masses are different.